In the absence of diffusion, a catchment concentrates the flow at the outlet, attaining the maximum possible flow at a time equal to the time of concentration. For rainfall duration equal to the time of concentration, concentrated catchment flow is obtained at the outlet. Since there is no diffusion, the method gives not only a peak flow, but also a hydrograph in the shape of an isosceles triangle with recession time equal to rising time. The runoff coefficient is the ratio of effective rainfall to total rainfall. A mass balance of effective rainfall and runoff leads to an expression for runoff volume V sub R. From which the abstraction-only runoff coefficient is in the absence of runoff diffusion, this runoff coefficient accounts only for hydrologic abstractions with a maximum value equal to 1. When diffusion is present, it may be accounted for by reducing the runoff coefficient below the abstraction-only value. This situation is applicable in catchments of very mild slope, say less than 0.0001. Diffusion increases the recession time and reduces the peak flow. Thus, a hydrograph cannot be obtained solely from the mass balance. The reduction in runoff coefficient to account for diffusion leads to where C sub D is less than 1. In practice, seldom is a quantitative distinction made between the two components of the runoff coefficient. For small catchments, runoff diffusion is usually negligible, leading to C sub D equal 1 and C equals C sub A. The runoff coefficient can be related to total rainfall intensity and phi index, assuming 1. Diffusion is negligible. 2. Total and effective rainfall are constant in time. The first assumption is valid for small catchments. The second assumption is implicit in the rational method. For catchment response without diffusion, for constant rainfall intensities, combining these two equations leads to solving for phi, the values of runoff coefficient may vary within a catchment. When a clear pattern of variation is apparent, a weighted value is applicable. Individual sub-areas are delineated and their respective runoff coefficients identified. Areal weighing leads to in which rainfall intensity is in millimeters per hour, area in square kilometers, and peak discharge in cubic meters per second. A composite catchment drains two or more adjacent sub-areas of widely differing characteristics. Assume two sub-areas A and B, with times of concentration T sub A and T sub B, respectively, where T sub A is substantially less than T sub B. Sub-area A has the shorter time of concentration. Therefore, concentrated or superconcentrated flow is assumed to start. Sub-area B has the longer time of concentration. Therefore, subconcentrated flow is assumed. An assumption of linear concentration at the catchment outlet of sub-area B is usually appropriate. Several rainfall durations T sub R, ranging from T sub A to T sub B, are tried. The duration that gives the highest peak is the design duration. The rational method is suited to catchments where drainage area increases more or less linearly with catchment length. If this is not the case, the peak flow may not increase with catchment area. For the peak flow not to decrease in the downstream direction, the drainage area must grow at least as fast as the decrease in rainfall intensity. For example, assume that the drainage area at A is 0.8 square kilometers and the rainfall intensity, based on the time of concentration, is 50 millimeters per hour. Assume that the drainage area at B is 0.9 square kilometers and the rainfall intensity is 40 millimeters per hour. Further, assume a runoff coefficient C equal 0.5. The peak flow at A is the peak flow at B is in this case, the peak flow decreased from A to B. This is because the product of rainfall intensity times drainage area actually decreased in the downstream direction.